Hi, my name is Patrick Berry, and I work here at the Kansas State Historical Society as a Senior Assistant Archaeology Administrator. I work on processing phase ones for highway projects, and I also am about to start my graduate work at Queen's University Belfast. Today I'm going to demonstrate the process of electrolysis for chemically removing iron oxide from iron artifacts. Would anybody raise their hand if they have any kind of background in chemistry? Somewhat? Okay,
all we did was take high school chemistry.
Right, okay, all right. Well, because I'll explain a little bit of what's going on and why it's important in terms of preservation to do work like electrolysis. So, but there's going to be some chemistry terms, and I'll try to make them as user-friendly as possible. So one of the things that one of my best science teachers I ever had would tell us is an important thing to remember in terms of chemistry is the following. If anybody can get this right on the first try, you get extra points. What side of the basketball do you dribble?
The outside.
The outside, that's right. It baffles high school students, but you know, the outside. And that's important to remember because chemical reactions only occur where there's actual contact for things to react. So when we think about that, there's a lot of times where I'm going to mention that as an important concept. So electrolysis, more or less, is the process by which we use a direct current through an electrolytic solution to trigger a non-spontaneous chemical reaction. Now what that means in terms of the application of archaeology is the removal of rust chemically using electricity. And so I have these in order of from when we started, and then we have the object when finished. And so I'll kind of go around the room. I'll pass these so people can look. And that's, as I held it, each day is a new photograph. Then finally we have this, and this right here is an axe head that we got from Pool Chief Village. As you can see now, a lot of the rust has been removed. It looked like, at the time, that it had almost been buried in a marine environment. Now, it's because it was found in a floodplain. And there's also other sort of variables. So when you have farming, people inject ammonia to give the soil nitrates. But one of the byproducts is that the hydrogen atoms, which are bonded in that molecule, as it breaks down into nitrates that actually affect the soil, the ammonia releases excess hydrogen, which bonds and forms acids, which raises the soil acidity, which helps break down and rust the iron faster. So you can kind of pass that artifact around there. Now, what you would need to do to sort of remove the rust with minimal damage to the artifact is electrolysis, which is actually pretty simple, but we've built a tank here that lets us work on up to 8 artifacts at once. I don't have all the wires present. I've got another one running that you can look at later, where you can see it bubble and the chemistry actually at work. So essentially what you need to do electrolysis is you need a non-reactive container. Plastic will work best. You just need something that's a resistor that will not conduct electricity. The next thing you're going to need is an electrolyte solution. What we use is sodium carbonate and water. And the mixture here that I'm using is approximately 30.25 liters of water to 118.29 milliliters of sodium carbonate, which is just washing soda, is what we use for the source of that. That's the most common, easy way for you to get it. The next thing that we need to do is create some anodes, which we're basically going to have 2 electrodes. One of them is going to be our artifact, and then we're going to have the anodes, which are positively charged in anything which is receiving energy. So if energy is going into it, the anodes are positive and the cathode is negative. So what we're going to use for that is just these pieces of iron rebar, which I always brush with a steel brush to clean off. And the reason is because what side of the basketball do you dribble? The outside. You need that clean so that this reaction can work. What we're going to do is charge these positively and run that current through the electrolyte solution in which we have suspended our artifact, which we will then make the cathode, which we will negatively charge. What will happen is that the oxygen, which is bonded with iron, will be stripped and drawn to these new sources through an electromagnetic process. Now, one of the things that we have to know, and why is this important, is iron artifacts are found very common, but iron is very unstable in its elemental form. And how do atoms become stable? Unfortunately, not through therapy. Instead, they develop codependent bonds, which psychology would say is bad. But at any rate, what does it react with? Well, basically anything. It's like a puzzle. So you have something that has a missing component in its outer shell of electrons, like iron. And it's looking for anything to fill those gaps. One of the most reactive substances is oxygen, which is found in H2O or water. the air around us, and so all carbon at all times is trying to become stable. And it will react with any oxygen it comes into contact with. If you add hydrogen to the mix, either through water or through the acidity of the soil or anything else like that, it eats away creating new surfaces for more iron to react. So the biggest problem we have with iron artifacts is when they get buried, especially in floodplains or anywhere here where we have high humidity and where people are pumping chemicals into the soil, you have this process of rusting. And although the iron looks solid, it has pits and cracks, so it has more exterior surfaces for the rest of reaction to take place. Those acids seep in, eat new, so it's an ongoing process. And unfortunately, though the iron is becoming more stable in a chemical sense, the artifact is becoming less stable in a physical sense. And that the iron is turning into a dissolvable powder of just ferric oxide, which we really don't want, because what that means is that given enough time, every single artifact made of iron will corrode and turn to dust. And then we can get no information from it. So this is the best process that we can do to remove that and suspend that, and then preserve these artifacts. So once we get going, we have these anodes that we've created. Then we use uninsulated copper wire, twist those around, anchor those in place. I've drilled some holes to help do that. Then we just use wire nuts, and we use insulated copper wire all the way around, leaving only two ends not connected to absolutely everything. One's the terminal end that's going to be just not used, not connecting or transferring power anywhere else. And the other is the terminal end, which we're going to be attaching our battery charger to, which is going to supply our direct current. We're using a 12-volt one here. Just kind of brought it out to show anybody in case visual aid helps at all. And then we're going to create a crossbar, and I usually use something that doesn't conduct. Wood works fine. I just use scrap lumber. What we need are just things that are in fact conductive, so what works good is steel. Not copper. Copper, if it touches the solution, which should never go high enough to touch the copper here or any of the copper wiring, because this reaction actually affects copper different than it does iron, and it causes a different form of oxidation, which actually makes it brittle and start to corrode faster. So it does the exact opposite of what it's going to do for our iron. But we use steel. Never allow stainless steel in the tank. And the reason for that is because stainless steel contains chromium alloys. Now chromium also is unstable, it tries to bond, but in this process it will bond with itself 6 times, forming hexavalent chromium, which is a very, very bad chemical to have. It's a very well-known carcinogen, and it's actually the subject of the Aaron Bragovich lawsuit. It's illegal to possess and illegal to dispose of. There's just nothing good to do with it. So make sure you're never using stainless steel during any one of these processes. What I've done is I've created steel wires here, which I allow that I can then hook more conductive material to. This one can let us do up to 8. We then have these little alligator clip insulated wires. I always code red for positive, black for negative, that way you'll always know. We have one conductive element here, which is our sort of rod, if you will. That's what I'm going to attach our negative charge from the battery charger to. And then I'm going to use this, and then we'll attach it to our artifact, not directly, but to the wire that we're going to wrap around it. So if you're done passing the axe around for a brief moment, I'll show you how we'd suspend something. And I can pull it out later, and you can look at it too, at your leisure. And this actually would need just maybe 1-2 more treatments, and then all the rust will be gone from the pitting pieces. And this will be returning, so you can see it more. So I've got just fence wire for electrical fence, good steel, non-stainless alloys. What we do is just find something, and because iron conducts well, and so does steel, all that has to happen is that they're making contact. You can put a secondary point of contact on there, it's all right, but just for the purpose of this demonstration, I'm going to create one thing. I just kind of twist it and create a natural hook. All right, rough one here, just for demonstration. Then put it through here. Because steel's touching steel, it will conduct. Then when we attach our negative charge, we have one to the wire, one to our direct source. Once we have the battery charger, negative, which is black, go to our cathode here. Need to give it a little more slack. I'm not going to turn this on. This process produces hydrogen gas, so use it either outdoors or with good ventilation, because hydrogen can be flammable. And we're going to attach the positive to our anode, just one of the ones that's not connected at both ends. Once we turn this battery charger on, the process would begin. You'd start to see bubbles, and that's when the oxidation is being reversed. As this goes, this water is going to become filthy. And then you're going to start seeing all this ferric oxide dust move towards these anodes, like they're being pulled by a magnet. So you'll see that in the tank that's active when you go take a look at it. Essentially, this is a very slow process. As you saw by the photos, day by day you're moving a little bit because, again, where do we dribble basketball? Only on the outside. So each time we begin to do this, we're only removing the outer oxidation. So to help it along, each day what I do is take rough steel wool, and with barely grazing the surface of the artifact, just brush. That'll remove anything that's going to flake away anyway. And that's the first thing that you do, is just get the bigger pieces off of it each time. It helps expose more for the process to work. Next, you can start moving to a medium, apply just really light pressure. And again, it's going to get rid of some of that dust, some of that powdery oxide. Then finally, when you want to polish it, you can use fine steel wool. You're always going to want to rinse with good clean water. Once everything's done, you're going to want to use like a hair dryer or a set of fans. Patting it off really doesn't work as well. You want to get this thing bone dry. Then you can use a microcrystalline wax, museum preservation quality like this one here that Virginia's brought. She's used before. And so you can kind of, I'll pass this around and see what it looks like. And then once we've coated that, what we've done is we've removed the exterior surface of iron from air exposure. So we've left it with no outside to touch, which suspends the actual point of corrosion. So then that artifact will be good. If you don't seal it with microcrystalline wax, you're going to have to repeat the process because any air, even that inside of a Ziploc preservation bag, can lead to corrosion eventually. And so if we want these articles to go on indefinitely, we have to preserve them. This isn't just for aesthetics. Now, one of the other things that I'll talk about is that we can notice something on our iron here that we have, this artifact. The oxidation isn't always sort of created equally. The different chemicals present can change different things. So one of the things we can see that's definitely present probably from the fertilizer used in the soil, but you'd usually find it in marine environments with salt water because there's a lot of chlorides present because the salinity of seawater is actually created by sodium chloride or salt. But those chloride ions, which are negatively charged, also impact the rate of rust. And so if those are present in the soil, you'll start to see it with greenish tints. So if you see any green on that, which there was originally, and you can definitely see it in some of the photos, that's the presence of chloride. And also probably the hydrogen-based acids that lead away a little further. So at this point, you should kind of have a basic idea of how this works, and I'll open it up for any specific questions that you have.
You were telling me the other day about what points first show cleaning.
Oh, yes. That's something that's really, thank you for reminding me. One of the things that's most exciting about this process for archaeology is that iron, though it looks solid, like I said, it has a pitted surface. Picture, if you were to zoom in enough, it would look like a sponge. Anywhere that's had good contact or working or wear, imagine you push down on that sponge and close those pits a little bit. You're compacting it. So wherever it's had tool marks or heaviest usage, that iron has less porous qualities at a microscopic level. So the first areas that clean are these compacted areas. So the first things that emerge as clean iron to us are where it was stricken, where tools scraped it, or where anything like that happened. So all of our tool marks, use marks, things like that, which we want to see, those are the first things we're going to see come out of that tank. Anybody else have any other questions?
So hooking up your battery charger to that, do you have to make sure you do negative charge first and then positive? Or?
You can do it in any order, and I should probably mention this is important. Whenever you're doing electricity, be very careful unless you have a lot of training. Just always use the right parts. Go to a hardware store, buy new. Don't scrap unless you're very well equipped at rewiring, just because it's easier and it's safer. So the number one thing I'd say is it doesn't matter which one, because I would never have this plugged in before I attach. I'd attach first, have this set to what I want it to be set at, then plug it in. So with a battery charger like that, and it's got a little plug. So these attached, what I do is I put the hood down, because we have a ventilation thing, and shut it so that it'll allow the hydrogen gas to be off. If you're outdoors, you don't have to worry about that. And then once everything's connected, I plug it in. And the only thing I'd ever do before touching this is unplug it, let it sit for a minute, and then there's very little risk of electric shock. But you are only working with 12 volts, so even if you did shock yourself, it's not going to actually kill you. It may hurt, but you know, you'll be okay.
Well, how many battery chargers do you need to do the turret of the monitor?
To do the, sorry, can you repeat that?
How many battery chargers does it take to do the turret of the monitor?
Turret of the
Three or
monitor.
four, you know, that's Civil War.
Well,
This is
I-
Civil War.
Civil
pretty
War.
submarine.
He's in the
Yeah,
Civil War.
the monitor.
Okay,
A huge,
how large is the artifact?
yeah.
But the big thing is that really you don't need a lot of electricity, you just need enough to help trigger the reaction. And so as this stuff, electricity works by conducting. So it doesn't matter how much iron you have in there or the voltage, or I mean, it matters more how much iron you have in there, not the voltage. So you still only need one battery charger for the object. But the way that this will best pull the old rust off your artifact is if you have equal to or slightly more exposed positively charged iron than there is negatively charged iron in the solution. But even if you don't, the reaction still works. You may need to clean your anodes a little bit, and you may need to clean your solution whenever it gets way too rusty. You'll see back there, it's pretty close with the one that you're going to see as a model. But it doesn't take that much electricity, because once you trigger the chemical reaction, it just keeps going. And it may work better where there's actual direct charge, and the reason is because rusted iron doesn't conduct as well as cleaned iron. So the cleaner it gets, the better the charge runs through the artifact. If that makes any sense there.
There's space there to hang 5 or 6 or 7 different artifacts.
Yes.
Can you do more than one at once?
Absolutely, absolutely. So like on this one, we could suspend up to 8, which I've allowed. And then I have 2 holes drilled to do auxiliary if I wanted to do 2 moderately sized ones and give them a little stronger support. Or we can use, you know, time for multiple ends and do 1 large one. And with this tank, that's pretty easily, you know, done. If you can't just easily wrap a wire around it, what you can do is get steel mesh like you get for a screen and create a basket to suspend something small in. And then make sure you have wires connecting from the 4 sides of that basket up. And as long as it conducts electricity, it'll transfer to other things which conduct electricity. And so we can suspend things apart and just use as much space in the tank. The only thing you need more is different wires, one for each thing you want to actually add a negative charge to. I usually put these here as anchors for the inactive wires if I have multiple wires on this at once. So if it's like this, it means that there's no electricity running anywhere and I just know that. And then this means that it's active, and I have that labeled on mine so that anybody that wants to use it knows what's on and what's off, essentially.
And so how do you decide which iron artifacts are important enough to do the electrolysis?
That's a good question. I would say it's not always a question of which ones are more important, but which ones are in worse condition. So the priority should be with ones which would be otherwise lost. When we first got this axe, it was crumbling in air, just dissolving bit by bit. If we did not intervene, eventually this would lose important information. So we stopped any further damage to these edges. So we can see where this got bent. We can see where this got chipped. We can see that at one point they were using this apparently as a hammer. But if we'd let that go too long, eventually we could lose and something here could break. These could be gone, rotted off. You know, those are kind of the things that I would consider before doing. It's just how bad is the corrosion or oxidation? Is it threatening our ability to have this artifact in the future? If so, that would be the top priority. Otherwise, it's just a matter of what side are you working on. You know, if Fulci Village is what you're working on right now, start there, look for the ones which are the most badly damaged and start there. And then, you know, in order, you got ones that are a little more physically stable, save them to later. Yes, sir?
Yeah, have you ever done anything like doing this electrolysis truck project with something like ultrasonic bath?
I haven't done that, but
Or have you heard of that?
there's many ways to remove iron oxide. Why I like to do this is because it's relatively low skill level, cost effective. So if you know enough about electricity that you're comfortable using, or you do a lot of that kind of work, I made everything in this out of scrap. Everything here cost us a zero balance. We had a plastic tank that was previously kind of used for this. We had a scrap barrel of copper wire, which I stripped, you know, to create the stripped versions and use the insulated. Used some old wire nuts, old nails, scrap board. So it's very cost effective. It's pretty safe in terms of all the different methods you can use, and it really doesn't damage the artifact whatsoever. So it's what I would use as a priority, just because it's very accessible to anybody, and even at a just low level of skill in understanding chemistry or electricity. You can follow, there's great things online for woodworkers. They usually often show with using the restoration of iron hand planers. So they show kind of like a sort of quick throw together in your garage electrolysis. A lot of people use that to restore their old hand tools. But electrolysis is powerful enough that it's also used to clean very large industrial engines when they get rusty. It's just a matter of how much metal you want to use, how you want to make it. You can make tanks the size of this room and clean things that are half the size of this room or more.
When that is done, when that piece right there is finished and all the rust has gotten, is pretty much removed, if we left it in the bath, it would not, as I understand it, it would not deteriorate the good metal.
Well, not right away. So the big thing is, like, what we do is if we have to turn it off for the night, I say just leave it in the water and I'll take care of it when I get in the morning, because I'm here only during the mornings and I leave halfway through to go to my other job. But ideally you'd be taking it out, drying it, whenever you're doing stuff. But if you're just continually leave it in the water in between stages. If you've brushed it off, cleaned it, it's not going to oxidize that fast in there, because you'll turn it on and it'll undo anything that just started. This powers rust off faster than rust happens, which is great, but it's not like it goes overnight.
I think Virginia's question was, the process only works on the oxidized part of the iron.
Oh, yes. Sorry, I thought you meant like when the machine is off.
Oh.
If the machine is on, there's no such thing as over-electrolysizing. That's the word. You can't do too much electrolysis. And the reason for that is because the reaction only works with the oxides. So once all the oxide's gone, what we're doing is not going to cause iron to detach its own bonds and magnetize to other iron. It really won't do that.
But you can have an artifact put in there that turns to nothing.
Yes, and that's dependent
So
upon
you-
the condition that it arrives in. So this one had density inside that was still good iron. It was solid, it had a core. So all we're removing is the stuff that would be lost to air anyway. So there's really no harm. And we're stopping that process from going any further. If you get something small, oxidized badly enough, or maybe found in seawater or something like that, or it was exposed to a heavy amount of acid, there's a potential that you could lose almost all of it. And that's because if all that thing is an amalgamation of various oxides just ready to be crushed into powder, then that's what's going to happen. So it really just depends on what you put in.